morning. So last time we considered or defined a specific class of constructible sheaves on graphs, spanning graphs on surfaces, which we called gentle sheaves, whose global sections describe, we noted, derived or mentioned derived categories of graded gentle algebras, and they satisfied some specific formulas. For instance, at every vertex, they assigned the derived category of the an-1 quiver, which we wrote in simplicial notation, and use an n-unit vertex. To every edge, they assigned the derived category of the field, actually the perfect derived category, and let me for today just write d instead of d perf. It's quicker, it's too many d perfs otherwise. And then we mentioned that so if you're on a disk, there's a unique gentle sheaf up to equivalence, and more generally, gentle sheaves are in bijection with line fields on the surface, which is some kind of grading information. So this means that as long as we're fixing a ribbon graph of a surface, we can kind of understand what kind of gentle sheaves there are, and this gives us, in this sense, a unique global sections category for a given graph. And what we want to understand first today is what happens if we change the ribbon graph. Do we get the same global sections or not, and how can we relate these different categories? This still falls in this part of macro gluing, of gluing categories, which we'll wrap up with this part, and then we'll come to the next stage of our gluing context, which is the micro gluing. So we will glue objects to get global sections and relate them with curves. So let's start with the
So can you say what a line field was?
A line field. So a line field is essentially it's a line at every it's a section of the tangent bundle, if you want.
Oh, okay. So it's like okay.
It's a line at every point. If you have an annulus, this would be a line field, the trivial one. Winding number is 0.
Projective.
Yeah, exactly. That's the correct definition. I wanted to be. Okay, so let's get to contractions. So a contraction of graphs is a local move as follows. So you take an edge of your graph and you simply contract it and you get a new vertex. And all the edges which are not the contracted edge remain. So actually there's one missing. And generally when you have a contraction, you're allowed to do such a move for as many edges as you want in any order, doesn't really matter. But the point is that any contraction comes from repeatedly doing this specific move. And if we're given constructible sheaf on G, and the contraction from G to G prime, let's say for simplicity, that we're just contracting one edge. If we were contracting multiple edges, we could just apply this construction multiple times, so we focus on this case. We now want to define a new constructible sheaf on, which is the push forward along the contraction if you want, which is then a constructible sheaf on G prime as follows. So how do we do this?
So one quick question, can we do this if there's parallel edges? Or only if it's
You mean this?
Yes?
Yes?
So you may need creating loops?
Well, then you create loops. We wanted to not have loops, but it wouldn't be a problem actually.
So the machinery works with loops?
The machinery works, nonetheless, you're not allowed to contract loops. If you contract loops, things break. It's just not true that the global section, we'll then see that the global sections don't change under this move, and this is not true for loops. So, okay, how do we do this? So, first of all, I'll tell you what we do at this vertex v tilde, since this is kind of where the non-trivial stuff happens. So we set C star of f evaluated at v tilde will be the pullback of the following. So we have f at v1, this goes to f of e, this goes to f of v2, and this goes to e. And we simply take the pullback here. And so this is kind of intuitively what you would do. You're just saying sections here are sections on, well, the pullback of the neighborhood, which is then the neighborhood containing v1 and v2, and you get that by computing the pullback. And then for, say, a vertex v prime not equal to v tilde, or an edge f not equal to e, you set f, C star f of v prime equal to f of v prime and C star f of f. Well, f is bad notation, let's call it e prime. E prime to be f of e prime. And similarly, all the restriction maps in the sheaf they are the same restriction maps as an F, and except, so what happens if you say, this is my edge E prime, then I have F of E tilde, I want to go to F, C star of F tilde, I want to go to F of E prime, and this has a map, so let me use color here. So if this is E prime, you have a map here to E prime, which you simply compose, and this is your new restriction map. It's a map induced or it's simply obtained as a composite. So for this would be E prime index, this should be E1, right? 1. And so kind of, yeah?
You told us this is all just factors on process.
Yeah.
This is right-hand extension.
Yeah, this is what we'll do next. Excellent comment. So, lemma, the global sections of F is equivalent to the global sections of the push forward. And the proof is a formal consequence of time extension theory. So you define exit of C from exit of G to exit of G prime by sending V1, V2, and V all to V tilde, and it's the identity on all other objects. They have the same edges and vertices G and G prime except of course these three. You have this map, and then in fact, or if you have a time extension, that C star F is the right hand extension, of F along exit of C. Yeah, you have to use the pointwise formula for kind extension. You compute it and you find exactly, essentially computing is pulled out. And then, what is global sections? So if you look at exit of G to exit of G prime to the point, if you take right hand extension along this one, so if you have C star of F, right hand extension maps it to its global sections. This is always true if you take a right hand extension of a functor to the point, you're simply computing the limit of the functor. And so if you start with F, you take right hand extension, you get the push forward, you take right hand extension, you get the global sections, and the composite is right hand extension, which means that this is equivalent to global sections. So this is the general result for constructible sheaf. It's not about gentle sheaves, it's always true that you can perform this constructing for constructible sheaves. And the crucial property now is the following, that F be gentle, then the push forward is also gentle. And let me sketch the proof. So we have these vertices V1 and V2. Let's say N is the valency of V1, M is the valency of V2. Then we can compute the valency of V tilde. So V tilde has the same edges as V1 and V2 except E. And E is counted twice, hence the valency N plus M minus 2 will be the valency of V tilde. Same edges except E, which is incident to both V1 and V2. So now you consider this push-out diagram from delta 0 to delta n minus 2, delta n minus 2. If you compute the push-out, you will get delta n plus n minus 2. This is n at infinity. And if you if you apply the functor, which takes functors into D, which is D perf, okay? Then you get functors from delta n plus m minus 2 to be functors delta n to be n minus 2, functors delta n m minus 2 to functors delta 0 to b. And this becomes a pullback diagram in cat infinity. Why? Because this functor maps colimits to limits. It's like a hom functor. Hom functor chooses limits in the first entry. And so what is this? This is f of e2. This is f of e1. And this is f of c star f of e2. And if you unravel this computation, you can check that c star f of e tilde, and not only does it give you the valency of the vertex minus 1 quiver at that vertex, all the maps are the correct maps. So it's really a gentle sheaf. But this is maybe the first thing we do in this computation. I'll leave the rest for you to check.
So you can also using the rotation invariance.
Absolutely, yeah. You can always use the rotation invariance to make sure that these two maps in the gentle sheaf are exactly induced from such an inclusion and such an inclusion. Where this is, say, the inclusion of the last vertex and this is the inclusion of the first vertex. And this is essentially pi 0 and this is pi n minus 2.
Yeah.
And
then you also see that the other maps are correct, right?
Exactly. Just yeah. I mean, you can do a very concrete computation. Question?
Are you also saying that the right connect extension preserves constructible sheaves?
Yes, it does here. The way we defined it, it does.
That's by definition.
Well, yeah, but I think it's also
So right connect extension on pre-sheaves.
on pre-sheaf. You can't say what a pre-sheaf is in this language. A functor of the exit category is already a constructible sheaf.
Oh, okay. So there is no sheaf.
The sheaf condition is, yeah, you basically, it's already encoded somehow. You already took the minimal data determining a sheaf via sheafification if you want.
Okay.
Yeah, that's the point of the exit category. Marius?
So you said e tilde is minus e n plus n minus 2.
Yes.
So shouldn't be the value of the gentle sheaf added like n plus n minus 4?
Yes, that's also what I wrote.
The fullback element is already
Wait, yeah, because n minus 2 plus n minus 2 is n plus n minus 4. Yeah. Other questions? Yes?
What happens if you create a loop? Can you say something?
Well, if I create a loop, I can't. This argument doesn't really. You would have to change the value, or if you do the same construction, you compute the right kind extension, your value at the vertex changes. Before it's an AN quiver. Afterwards, it's some kind of polynomial algebra, something which is not finite dimensional, and so you're leaving the world of gentle sheaves if you collapse loops. That's maybe the reason we don't want to do this. If you create a loop,
Yes.
you can't create a loop. You can only contract loops.
No, but if you have parallel, if you have parallel edges, so
Well, nothing bad happens. I mean, it's just the same construction as if the loop. It wasn't a loop, but I mean, if you have this situation. This construction is the same as if these two were external edges, and then afterwards you identify them. Nothing new happens there.
Just to go back to the loop question, so you said you get like polynomial algebra, but you can still maybe see this as like generalized gentle but infinite dimension. So is that in the direction of why this all still works when there are loops?
Well, yes, though I would never contract loops, I think. This is also not necessary. So there's a result that any two ribbon graphs, any two spanning graphs of the surface can be related by a zigzag of contractions. So let me write this here. Fact, any two spanning graphs G and T prime of our fixed marked surface S are related via a zigzag of contractions. So So you would start with say G, then you have some graph G1 to which it contracts, then you have G2, G3, and so on until you end at G. So you can, and you don't need to contract any loops for this statement. Also, the homotopy type of the graph and hence of the surface changes when you contract loops, and we don't want to. You can of course do these things, but then you're kind of leaving this very nice realm where things are very straightforward.
Because loops are not contractible, don't contract.
Exactly. Perfect.
What?
Yeah, also, yeah, the point is also this is maybe one thing I didn't say here. If you're contracting an edge, this is still a spanning graph. You're not changing its homotopy type. Okay. And the consequence of this fact that you can get from any graph to any other graph via zigzag. I mean, you get then a gentle sheaf here, it comes from a gentle sheaf here, it goes to a gentle sheaf here, and so on. And every time you get an equivalence of global sections, you get the following theorem. Let S be a marked surface with line field. Let G and G prime be spanning graphs. And F prime gentle sheaves on these. Gentle sheaves on G and G prime. Such that the corresponding line field is, let me say, compatible with the line field, or inducing the line field. Then the global sections of F is equivalent to the global sections of F prime. So we get if we have a surface together with grading information, there's a unique category we get out of this gentle construction. And this is called the topological Fukaya category of S. And the way we have defined it, this category is now determined up to equivalence. So it's not you're not really constructing a category, you're constructing an equivalence class of a category. But there is in fact a refinement of this construction, so there's a refinement.
So you just
yeah.
you explain how to map sheaves one way.
Mm-hmm.
You're saying you can also.
I can always find a pre-image, yes, in this construction. I can just choose any gentle sheaf, and then because I know that gentle sheaves are unique up to equivalence, once I fix the grading information, I'd have my gentle sheaf on the contracted graph. I choose any gentle sheaf on the bigger graph with the same line field, then I contract it, and then the two will be equivalent, because gentle sheaves are unique.
But it's not clear that this is independent of this.
No, absolutely. So some of the homotopy type of the surface, they may be non-trivial equivalences you're getting out of this construction. And what I'm about to say is that there's a refinement of this construction, which makes such that the result is unique up to a contractible choice, which kind of needs a different language. So refinement, this is due to Dukhanov-Kapranov. And basically I'm reformulating that construction here in sheaf theory, because sheaf theory is very concrete, it has that advantage, but it gives a slightly weaker result. And this uses, they're using language of cyclic two-Siegel objects, or potentially paracyclic. They say that this refinement makes the construction unique up to contractible choice. So there's an interesting aspect of the category of spanning graphs and contractions. This category is contractible. So using the fact that the category of all graphs is contractible, and thinking hard, you can prove that this result actually, there are no paths you can take with going through different contractions and getting different equivalences. They will all be homotopic. So.
Does this give you a functor in surfaces with line field?
Yeah, there's no, if you change the line field, there's no functoriality anymore. What you can do is you can change the mark points. But, yes, question?
Is there any way to prove this by defining Fukaya category just using S as an input without going?
As what is input?
Can you just directly define it only using the surface, like in geometry, like some of these?
Yeah, there's symplectic definitions, like intrinsic to the surface if you want.
Okay.
Yeah.
I don't know if you have time, but can you like explain once more how this line field, how did the line field induce like the gentle sheaf? Like how do
the gentle sheaf determined the line field and was basically these shift functors, which change. So this is explained in the lecture notes. It's kind of complicated. Okay. You can always extract certain. So if you have a loop in the surface, you can always construct certain autoequivalences of the derived category of the field by going along this loop and taking certain functors and adjoint functors in the sheaf. Which specific ones is explained in the lecture notes, called as transport, and it's like parallel transport along the sheaf. And once you do this, you get autoequivalence of the derived category of the field, which are just shift functors, and these shift functors give you numbers, and these numbers relate with the line field. Okay. Yeah. So it's a bit of a complicated story. Other questions? Okay, then a few remarks. So we have been working over a field. Same construction also works over any base. So same construction works with coefficients in any stable infinity category. So for instance, you can define the spectral Fukaya category of the surface using this construction. And in fact, this uniqueness after contractible choice statement was also proven by Jacob Lurie in his paper on rotational variance of K-theory. I think it's called Lift to the Spectral Setting. So yeah, you get you can also get a uniquely defined category for any coefficient category. And another remark, in construction works, if you have coefficients in, so very special case is the two periodic coefficient case. Two periodic coefficients, which roughly means that the identity is a shift by 2. In the spectral setting, this is not the correct definition, but let's not worry about this detail. So if your coefficients are 2 periodic, if you remember this rotational symmetry we discussed of the gentle sheaf on the disk, there was a shift by 2, but there were no shift by 1. So if shift by 2 is the identity, rotation is a strict symmetry of your gentle sheaf on the disk, and there's a preferred construction of the topological Fukaya category, which only takes as input the orientation, and there's no choice of line field. So I have a preferred construction. This corresponds to a line field with all winding numbers even. Winding numbers even, and you thus get a topological Fukaya category associated with any just oriented surface, or just oriented model surface. And the two periodic case is actually is also relevant for practical applications. For instance, let me mention one. So, for instance, if you have the if you choose D to be the your coefficient category, to be the one periodic derived category, this is a 2 periodic category. The shift by 2 is the identity. And then you get the one periodic topological Fukaya category, and this actually appears in relation with cluster theory. So you get the one periodic topological Fukaya category. This is the orbit category. It's the you take the z action given by the shift function to take the quotient. The one periodic topological Fukaya category. In some work of mine, I explained how this category relates, gives an additive categorification. Categorization of cluster algebras of surfaces. But I just wanted to mention this because it's an example of a two-periodic topological Fukaya category that you can use for actual applications in representation theory, if you want, related with cluster algebras.
So it's called one periodic or two periodic?
It's called the one periodic category, but
okay.
it's
so
two periodic. Yeah. Its objects are one periodic. It's like one periodic chain complexes.
Right.
This is always a hassle. Like this question comes every time. Okay, so let's wrap up one here and come to the global section from curve story. Unless there's questions.
Does this produce anything meaningful for topological?
You're asking the case theory of the category, or?
Yeah, sure. But for the coefficients, I want KU modules. This would also satisfy.
You can take any stable category.
Yeah,
This construction somehow is then, yeah, it's.
I mean, KU has the nice property that it's periodic.
Yeah, sure. At the infinity. Yeah, you don't need this, but you can have it. I mean, it doesn't hurt.
Well, just asking if there's anything.
Yeah, so far I haven't found any specific meaning of that statement in this context. Okay, now microgluing. And so last time we learned about, first let me a few definitions. So recall indecomposable objects in the derived category of the great gentle algebra. They are in bijection with curves in the surface, which are equipped with a grading and a local system closed. The system closed. So in these topological Fukaya categories, you can classify all the objects combinatorially in terms of the surface and some mild algebraic data. And we'll now want to construct these objects. I won't reprove this this classification, though you can do this with sheaf theory as well. Let's now first do something simpler and just construct these objects. So S is a marked surface. The simplest types of curves you can have are so-called arcs. An arc in the surface consists of an embedded curve, gamma from 0, 1 to the surface, such that, first of all, the endpoints lie on the boundary of the surface without the marked points. Gamma does not intersect the boundary otherwise. And we're forbidding the following pictures. So if this is your marked surface, marked points, this curve is not allowed, it's contractible, and this curve is not allowed, it's contractible. So gamma not contractible. And arcs are considered up to homotopy. I won't write this. So Another definition, what's an arc segment? Choose a triangulation of S. Triangulation of S. Then an arc segment in S is an arc in a triangle. So it's basically the same conditions, except that the endpoints don't lie on the boundary necessarily, but they lie on one of these triangles of the surface. So I can draw a picture. Say this is our triangulated, what is it, a 5-cone? This would be an arc. So arcs will always be noted by delta. So this would be delta, say 1, this would be delta 2, and this would be delta 3. They're all perfectly fine arc segments, and if you compose them, you get an arc, gamma. And so the remark is every arc is the unique composite of segments. Gamma is delta 1, delta S. It's a simple topological fact.
The triangulation that is somehow transverse to the arcs.
Yes, you get the arcs by intersecting the curve with the triangulation. If you want. I mean, you have to choose a representative of the curve, which is kind of good, and then you intersect them, and then you get everything. These curves are all considered after homotopy, fixing the endpoints if you want.
And that's why your unique is unique, like.
Right, because it's an equivalence class. So I didn't write this in arc equivalence class under homotopy.
Do you allow also intersections of S, right?
Say again?
Self-intersections of S?
No, I want to embed it. Just for simplicity, you can have this. In these curves, which classify objects in general algebra, they are not embedded. They can have self-intersections.
Okay.
This can all happen. We're just doing here the simplest case where everything is going to
Okay, sorry.
I'm just not going to bother explaining that.
Is the triangulation somehow minimal?
All triangulations have the same number of the edges of the triangulation have endpoints with the marked points.
Ah, okay.
But then, like a unique small minimal or something like that. I mean, this is not a unique.
All triangulations have the same number of edges.
Yeah, but the arc segments, it's going to be, there's a unique minimum and one unique.
Well, I'm saying that I'm not allowing them to be contractible, and by removing this, I get that they are unique actually.
So the triangulation is the
Oh, and they're not contractible.
Yeah, I'm forbidding contractible ones.
so marked points. The triangulation is on marked points, and then like an arc that just jumps a marked point is not contractible, right?
So if I have say I look at this arc and I deform it to this arc and then intersect it, then this becomes contractible. So I would not allow this. I'm choosing a representative of my arc such that all the segments are then non-contractible, and then it's unique. That is the precise statement. Yeah. And maybe one remark, which is important. The triangulation is dual. Triangulation is dual to a spanning graph. Dual to a three-valent spanning graph. Okay. Now let's look at the triangle. We will be gluing, so we need to understand the local case very well, and then everything else will be very formal. So if you have the triangle, these are all arcs in the arc segments in the triangle, right? There are exactly three arcs in a triangle, and they match the three indecomposables in functors from delta 1 to d, where d is the perf of the field. Which indecomposables are this? This is k goes to k, called it S2. This is 0 goes to k, which we called S1. and there's k goes to 0, which we call S0. So the number of arcs in the triangle matches exactly the indecomposable objects in here up to shift, plus shift. And this is exactly what it means that we can classify. In the case of the triangle, this is exactly the classification of the indecomposable objects of the category in terms of arcs or curves. All the curves which you allow in the triangle are these three curves, and then you put a grading on them, and you get exactly these three objects up to shift.
So you pick picking an ordering of the vertices or something like that, and then does your cyclic.
Yes, exactly. Everything is cyclically ordered. This will now be very important. Absolutely. So this I erase, and then let's now choose a specific gentle sheaf on the triangle, and then make this matching precise. I mean, I haven't said which arc matches which object, right? This is now important. How do we match them? And everything will be cyclically invariant. Hence, there are essentially two choices. But which one do we make? So we choose FV. V is a trivalent vertex. So this is V, this is E1, this is E2, this is E3. FV will be functors from delta 1 to D. This is fiber 0, 1, this is D, this is D, this is pi 0 shifted by 1, and this is pi 1. So this was our gentle sheaf model on the triangle. And let us compute. Let's do a small computation. So if you take f, v, from v to ei, of say 0 to k, what you get, so if I have 0 to k, if I take pi 1, I get k. If I take the fiber, I get k minus 1. And if I take pi 0, I get 0. So this is I is equal to 1, I is equal to 2, I is equal to 3. Let's compute the next one. Fv of from v to ei from k to 0. This will be, so pi 1 will be 0. The fiber of this map will be k. And pi 0 shifted by 1 will be k shifted by 1. That's equal to 1, 2, and 3. And the final computation Fv from v to I of k identity k. While pi 1 gives you k, the fiber gives you 0, and pi 0 shifted by 1 gives you k shifted by 1. This helps us match the three objects with the three arcs. How do we match them? Let's this was B, this was E1, E2, E3. So let's call this delta 1, this delta 2, and this delta 3. The three arc segments in the triangle. So delta 1 goes from E1 to E2. Hence, we choose this, we say this corresponds to delta 1. And then the second one, it goes from 2 to 3, which is delta 2. So we say this is delta 2. And in this one, we say it's delta 3. This is how you match them, and you see that the values where it's non-zero, this functor corresponds to the curve. The curve describes the support of this object. We'll understand in which precise way in a second. So let me write one thing, and then we get to that. So let's define L delta I tilde V to be, so what was this? This was S1, this was S0, and this was S2. So we set it to be S1, S0, S2, I is equal to 1, I is equal to 2, I is equal to 3. And this is in f of V, which is functors in delta 1. So this defines us a local section living on the stalk. And now we want to turn this local section into a lax section. A lax section is a section of the Grothendieck construction, and we then glue these lax sections to produce a global section. So, how do we do this? We need more Kahn extension. So, remember, we have our sheaf F. In fact, it's a strictly commuting diagram. It factors through the nerve of simplicial sets. And we have the Grothendieck construction of this factorization, which is a fibration over exit of G. And now we want to take the Kahn extension in this context, which is relative with respect to P. So this is a generalization of usual Kahn extension. It's a bit technical to unravel. It's quite the long definition if you look at it, say, in Caradon. Let me just briefly explain a few things about it. So let's say we have a vertex of exit of G, and we have a local object at the stalk, such as one of these three. Then what we have is we have xv living in f of v, which is a subcategory of gamma of f. You have the map from delta 0 to exit of G, which is the inclusion of the vertex v. Then you have here the identity, and here you have P. And the P relative left Kahn extension is the universal lift in this diagram. And what is it? It's a lift. In particular, this commutes. Hence, it's a section of P. And this is sections of P. The category of sections of P, we call this like sections. Like sections. So, yeah, there's a coincidence somehow. One is a section of a map, and the other is a section of a sheaf. And the fact that it's both a section is a coincidence, but it's just to why this is two types of sections at the same time. It's a coincidence. Terminology. So how is this relative Kahn extension defined specifically, giving us this desired lift and the lax section out of the local section? So you take the left adjoint of the restriction functor from, this is sections, right? Functors from exit of G to gamma of F over exit of G, this is exactly sections. And then you restrict such a section at V, you get a functor from delta of 0 to gamma of F, which maps, which still lives over exit of G. So what this means is that you're mapping the point here, the vertex of the zero simplex, to an element living in the fiber over V. So in this fiber over V of gamma of F is exactly F of V. So there's a lot of notation here going on. Point is you can restrict lax sections to the values, and they give you the value of the sheaf. And this functor has an adjoint. It turns out a left adjoint, and this is called the P relative left Kahn extension functor. It's a functor from local sections to lax sections. This is very abstract. I can draw now a picture, which will have a very concrete. So how do I compute? How to compute ln P of xv? So there's a pointwise formula for relative Kahn extensions. We won't be discussing this here, but if you unravel this pointwise formula, you get the following. So let's say you have here V, it has E1, E2, E3, and then you have some other edges, say V prime, V double prime, then V4, and so on. This is your exit category. Now, if I draw ln P xv, here, first of all, if you evaluate at V itself, you just get the object back. Kahn extension and restriction in this case is the identity. And then, to go to, say, E1, E2, and E3, what I do is I apply the functor f from V to E1 of xv. This is f of E to E2 of xv. And this is f of V to E3. And these morphisms, they are coCartesian. Cartesian. So this is how you compute the left Khan extension, say close to the vertex, and then everywhere else it will be 0. So here you then get a map from 0, 0, and so on. Here you get a map from 0, 0. So the way you have to imagine this left Khan extension is that below the vertex, you're taking the coCartesian edges, which just correspond to applying the restriction map in the sheaf, and everywhere else, say at V double prime, there is no map from V to V double prime, and they don't talk to each other. There's no way to universally go from here to here, so you just put 0. This is what this does. So these values here kind of now tell us the evaluations of the relative Khan extension at the different edges. This is exactly what we computed on this board. Well now, let me draw this again in an example. Then it will become immediately clear how we can glue these like sections to global sections. Example. S is the foreground, and this is G. Triangle standing graph. And let's say the vertices is this, with the vertex V1, another vertex V2, here an edge G. Then we choose our gentle sheaf, which we can choose as follows. Functions from delta 1 to D, 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 factors, delta 1 to D. By the way, D here is the derived category of the field, but if it wasn't, say another stable infinity category, I mean, this construction doesn't really use that derived field. So you can write down everything in the same way. Fiber, chi 0, chi 1, chi 0, fiber, chi 1. This will be a gentle. This is a gentle sheaf, yes. Perfect. So then, right, we define for delta I segment, an arc segment, L V delta I as the pure relative left Khan extension of L tilde V delta I. Where L tilde V delta I was defined over there. So this will be in f of V, where here either V is equal to V1 or V2. So we take these local sections and we put these lex sections. So let's say, let's choose a specific, this is our triangulation, dual to the ribbon graph. Let's choose a specific arc composed of two specific segments. So let's say it's this arc. So this is delta 1, this is delta 2, and the entire thing is gamma. Then what is, let me write it. So L V1 delta 1, this will be k goes to k. So this is the value at V1 here. Because delta 1 goes from here to here, which corresponds to going from here to here. So in this section, the value x is 0 here, the value x is k here, the value x is k here. So these values here are obtained by applying the restriction maps. So they are coCartesian edges, all three of them. Let me indicate coCartesian always by an exclamation mark. And then here you would just have 0, 0, 0. And these two are coCartesian by chance, but this one is not coCartesian. So this section is a lax section, but not a global section. And let me erase this board and then write. Like this. There's another way you can think of these sections. You see this diagram is somewhat the same diagram as the sheaf itself. You can, if you want, to draw all of these elements inside of the sheaf picture. As follows. You have k goes to k, gets mapped to k, gets mapped to k, gets mapped to 0. Here would have 0, and this does not get mapped to k. This would be your section. But there's a universal map from 0 to k, which you use to define the section.
Can I ask a quick technical question?
Yes.
So you explained already last time that you could interpret, for example, this category of arrows as a category of fiber sequences and so on, right? So you could replace the values of your sheaf for these cells of the S construction or paracyclic S construction, where you choose iterated cofibers of full maps and their sheaves and so on. And it seems, so I just wonder, if you would have written everything like this, would it have been easier maybe to exhibit the cyclic symmetry of Fukaya and so on, like these lemmas would be even easier to check?
In some sense, yes. In some sense, it's more as equivalent what we discussed.
So at the end, so I was curious about whether there is a material advantage of choosing one presentation of the stocks.
It's very easy to say what a gentle sheaf is. You can just give the definition, and you have an easy definition, and you have to do the work afterwards. This, I thought,
this one?
Yeah, I think for didactic purposes,
so from a calculation perspective, this is advantageous for us. I see.
Okay, so we have, let me write this section again. So L, E, delta 1 will be 0, K, 0. And then you have another section, which is L, V2, this is V1, vertex 2, delta 2, which if you, this is delta 2, if you compute what it is, you will get the following. You will get 0, 0, 0, K goes to 0, K. So you take K goes to 0, and you apply the fiber, you get K. You apply pi 0, you get K. You apply pi 1, and you get 0. Okay, and then let's look at this diagram. How do we glue these two sections together? Well, we have to glue them here and here. How do we glue this? Well, we look at the section, which is of the form 0, 0, K, 0, 0, 0. So everywhere 0 except at K. It's, if you want, the left conic section of K along the inclusion of the edge into the hexagon. So it's also a conic section, but this time from an edge instead of a vertex. And this includes here, and it includes here. So I have to see that there's a map of sections from this section to this section. So this is a diagram inside of the category of lax sections. And then if you compute the pushout, so there's a very nice feature that pushouts in the category of sections are computed pointwise. So if I say I want to compute the value here at this vertex, I'm taking the pushout of 0 with 0 and 0. So I will get, let me draw them like, what do I get? So I will get a diagram of the form 0, K goes to K, K goes to 0, K, 0. And this diagram is now coCartesian. Right? These were all coCartesian. And taking in the respective diagrams, and taking the co-limit, so the pushout is computed pointwise in the next option. Taking this pushout, I'm basically taking the union of this section in this section, and the only time I'm really taking a push-up is of k with k along the identity with k. And I get k. So somehow, and this will now be in global sections. It's a coCartesian section, hence it's a global section inside of like sections. And we call this the global section associated with gamma, x gamma. Global section associated.
How are those shifts? I mean, can shifts appear or not?
Absolutely. Let me draw another one to get some intuition. Shifts can appear, of course. I kind of chose this one so it doesn't. We're always free to choose our gentle sheaves, right? As we kind of spent 1.5 lectures justifying. Also, doesn't matter this construction which ribbon graph you choose. You can always get all the objects from this construction. So another example. If we have this was gamma, and this is gamma prime. Then what is the coCartesian section corresponding to gamma prime? So x gamma prime will be, I have to check my notes. It will be 0k, k shifted by 1, 0, k shifted by 1, k shifted by 1, 0, k shifted by 1. And again, it's a coCartesian section. So there's an important thing to observe. Note the support of x gamma for gamma in arc. So this is, what is the support? This is the x and x set of g, where x of gamma of x, let's say y is not equal to 0. This is exactly described by the arc. For gamma arc is described by gamma. So if you look here, somehow the part where this section is non-zero is exactly this part, and this has the shape of an arc, right? And it's exactly this arc in this arc. Where if you embed, you can embed this triangle, this diagram inside of the plane, and then you can really match how the coCartesian section looks like with the picture you draw. So from the sheaf language, curves are somehow very natural. And you get this, you get this algebraic interpretation of this geometric picture in terms of sheaves.
A general surface is more complicated than the square.
Right, but it still works the same way. So here we glue two arc segments into one arc. If you have 3 arc segments, you just take one more push out. If you have 4, you take one more push out. If you have 5, you take one more. And then what do you do if you have a closed arc segment? You do this construction until you come back where the two close up, and then you have to identify the two ends. And there you have a choice. And this choice is, if you're one-dimensional, it's an invertible number in the field. And this is then the local system on the closed curve. So this is how you can construct also from this technology closed curves.
And this comes from the line field?
The line field?
No.
So the line field.
But I mean this number.
Yeah. So if you look at this,
okay,
here we start here with a k, and then we go along the arc and we come out with a k. And here we start with a k.
Yes.
We go along the arc and come out with a k shifted by 1. If you have a closed curve and you do this and you go around, you get the winding number of the line field.
Yeah.
If it's not 0, then it doesn't close up.
Yes.
and then you don't have an object.
Ah, okay, okay. Yeah.
This is also just how it works in,
Yeah.
unless you're, say, in the 2 periodic version or the 1 periodic version, then you can always close up. Well, 2 periodic if, yeah, no, actually also in the, well, if in the 1 periodic version you can always close up. In the 2 periodic version you have to then be sure that, well, there's either you can close up or you're shift by 1, but you're more likely to be able to close up. Let's say like this.
Sure.
But you're saying in one case this is unit in the field, the other case you need this shift to.
So if I suppose that this was the annulus, not the disk, then this would be the same. This point here would be the same point here. And if I do this construction, my value is actually the sum. And then I would basically take a co-equalizer of the 2 inclusions of k here, but I cannot in this case because they are different. So if you're, let's draw an annulus. If this is your arc, which closes up, then you do this construction until you come around. So you're like looking at a curve with 2 endpoints which are the same, and then you're producing a coCartesian section which is, it's say k plus k shifted by n here, and it's in here it's k, and so on. And somewhere you pick up the shift, and if these 2 shifts are not the same, then you can't join the 2 ends, and you don't get an object for the closed curve.
So can you say precisely where your obstruction is? I mean, there must be some obstruction group where you.
It's not an obstruction group, it's simply an algebraic condition about the grading of the surface.
But so is it the correct picture that you have this line and you go with it and then it kind of turns to like the opposite kind of line? So
Right.
you cannot glue them because you started with this direction, but when you go around the curve you kind of end up with a different
But you say usually obstructions to gluing, why is the obstruction to?
It's not a very deep obstruction, it's simply 2 numbers being the same.
Yeah, but
Or 1 number being
but you
0.
also have something like a K star came up as sort of the needless obstruction. I mean, it sounds like that's it.
So how they do it, yeah, no, it's not, no, this is about uniqueness. If it's possible, then there's always a k-star family of possible ways, and this corresponds to identifying this thing with this thing.
Right. No,
And
I'm
so-
just saying there should be a spectral sequence where these obstructions came up, right?
I am sure you can get that.
So if your field is not algebraically closed,
Yes?
you would expect some irreducible polynomials to appear
Uh-huh.
to classify objects. How can you see this appearing? Because this, of course, what you say is so topological that it's not sensitive to properties of the field works already here, right?
Yeah.
So if you can really classify all objects, so for example, so how does one
Well-
can see this here? Or?
Let's see. I mean, it's essentially about with one of the auto. If you're looking at like in fact, so if you're 1-dimensional, it's easy. It's just an invertible number. But if you're higher dimensional, say, so what you can do is you can do the same construction, but instead of starting with 1 arc, you start, say, with a double arc. And so I would have 2 arcs, and then I have a k times 2 here, and k to the n times 2. And now I'm identifying k times 2 with k to the n times 2. If n is 0, I can do that. And then I have a 2 times 2 matrix, invertible. But actually, the matrix doesn't matter. Only the, what is it? The conjugacy class of the matrix, I think. And then the question, what is that? Depends on the field. Like sometimes there's Jordan forms, sometimes not. But I mean, there's a general answer for any field. And if you're algebraically close, there's a nicer answer. What do you mean by this question?
I mean, you have compute K1 essentially to accept that. Maybe let's
Okay.
look up
Yeah, let's talk about this later. Yeah?
And I don't really get how did you choose this number? I mean,
The numbers
So-
here, how
Yeah.
it shows them.
Yeah.
So, okay, if you make this systematic, your objects are not arcs, they are arcs graded relative to the grading of the surface. This is how they do it in symplectic land. So you have this line field, and then you choose another line field on the arc, and then you always remember how you also choose the homotopy between the restriction of the line field to the arc and the line field you chose on the arc, and this is called a grading. There's always a Z family of such gradings. So essentially it corresponds to this construction or shift of this construction, but everything is formulated intrinsically. And then, yeah, you get a condition that then certain number which you get by going around the arc, say 0 if you want to close it up. And here, where do these numbers come from concretely? I mean, this is just how I chose my sheaf. I could have put here shift by 3. Then something else would have happened. This is my choice. I'm choosing one specific gentle sheaf, but the point is on the disk, all gentle sheaves are equivalent. So it doesn't really. You have to think about this as me choosing coordinates. There are choices involved, and this is not an intrinsic way to present my objects. It's a way to present my object once I've chosen this coordinate system.
So it's like choosing a generator of the global sections, or the category of global section.
In some sense, you can. Yeah, in some sense, yes. Maybe one remark, which is very important, is that this is where we're using that we have sheaves of categories and not co-sheaves of categories. If you go to the literature, say Haydn, Katsakov, Komtsevich, or Ganatra, Padenschende, they all use co-sheaves. And co-sheaves have other nice properties, but the property of sheaves is that you can glue global sections in this pictorial way. And this is what is very nice about sheaves, and this is why I would advocate to also use sheaves, not only co-sheaves. Yeah. Okay, question?
So if you fix a gentle algebra, then you sort of have a T structure floating around. Can you describe like what the curves look like with respect to that presentation? Like
You mean the ones in the heart?
Yeah, or what does the T structure look like if you do it as picking a presentation of this kind?
That is a complicated question. It's already saying which object's in the heart. The answer is already not very pretty. Yeah?
So from the gentle perspective that I talked about, we glue the surfaces from polygons. And here it looks like we glue the polygons from triangles up again.
Yeah.
And so there are no relations. So what happens? So how do I see in these gluings that there should be a zero relation in my corresponding gentle algebra?
Excellent question. So the gentle algebra in this case is the A3 gentle algebra.
No relation, so
and what generators correspond to what? So if you have the A3 quiver, this corresponds to this. This gives you an A3 quiver. Morphisms are computed by boundary intersections. And then this is A3 without relation. If you want A3 with relation, you would take something like this. And then this intersection are different boundary components.
Yes.
And this gives you a relation. And you propose.
Maybe for those of you that were in the lecture by Jan, this version of the geometric model is kind of cosine or quadratic rule to the other, so they actually not compatible. I mean, they're compatible to quadratic rule. So
it's different.
In the opposite way.
Yeah.
This one would have been no relations and the other.
Yeah. Okay, in the last lecture, we'll play around with if you have a local section, how do you produce out of it immediately the global section? This is called induction, and then look at a more general context of sheaves of categories called published rules.